So now we come to the second half of the lecture today, and that is about the origin of atoms, which has to do with the Higgs boson. And when you look into outer space, much of it seems completely empty, of course. But the idea here is this particle called the Higgs boson is frozen into this empty space. Everywhere you go, there must be tons of Higgs bosons, and that's the idea, and that is actually very needed for us to understand the origin of atoms. And this became a big story worldwide on newspaper. You may have seen that even front page articles about discovery of the Higgs boson. And that came out from an experiment called Large Hadron Collider. There's a laboratory that's an international research center called CERN, which is on the border between Switzerland and France. And they have built this big tunnel, which you can't actually see in an aerial photograph. It's painted on, it's underground, which is as big as 27 kilometers in circumference. It's a big, big tunnel, which is filled with high-tech equipment. You may appreciate how big this tunnel is by comparing the size of the tunnel with the size of the Geneva airport down here. And the basic idea is that by building this big experiment, you can accelerate particles like protons to an incredible speed and energy. You can smash them together and recreate the condition of the Big Bang. So we're trying to basically redo the Big Bang. We can't quite do the Big Bang, of course, but maybe we can do a little bang that we can study what kind of reactions happened back at the very beginning of the universe. And if you go inside the tunnel, you see something like this. Now, all of these things are very high-tech components, and you can barely notice the tunnel is curved because it's such a big tunnel. And this kind of particle accelerator, you may think is some very unfamiliar special objects. But if you actually go look around, for example, this is a map of Japan, you find actually many, many accelerators in the country, and most of them are actually hospitals. If you do cancer therapy using radiation therapy, that's when you use particle accelerators. A lot of imaging devices used in hospitals that you can actually sort of scan your body through and see what's going on in your body. Many of them also rely on particle accelerators. And some older people among you might have actually had a particle accelerator at your home at one stage. That's the old TV set. And TV set actually accelerates a beam of electron towards the screen. When the electron beam hits the screen, it lights up, and that's what we saw on a TV screen. So there used to be one accelerator in every household in those days. And what they have done is they think they have created this new particle called the Higgs boson, but they actually decay immediately. So you're only looking at sort of the fragments of the Higgs boson at the end of the day. But it was so exciting also to myself because it was a long history behind it. When Mr. Peter Higgs proposed this idea that universe has this Higgs boson stuck everywhere, and that was already like 50 years ago. People started contemplating doing an experiment to prove this theory that was like also 30 years ago. And people started building this humongous experiment like 15 years ago. So it has a lot of history behind it. That's why it was so exciting and moving to many of us. And just to show you the complexity of this particle accelerator, so you start with a proton produced at one stage, and it's just a strip of hydrogen. And then you put that into the first set of accelerator built in 60s and 70s. You start going up in energy. Then you go into the super proton synchrotron, which also did a very good discovery in the 80s. And eventually comes into this biggest accelerator, Large Hadron Collider. And proton beams go through this big sort of pipe. And because this is an international experiment, at some point you see that we cross the border from France to Switzerland inside the tunnel. And what's accelerated inside, as I said, is the proton, which is made of 3 quarks inside. It's a fairly complicated object. And you bring them together at the end of the day, smash them against each other. That recreates a kind of phenomenon that might happen right after the Big Bang. Then you start producing a spray of particles after the collision. And most of the particles that come out didn't exist before the collision. So that's again E equal mc squared. You can convert this collision of energy into the production of mass at the final stage. And what you see in this case is 2 particles of light called photon, which we believe is a fragment of the Higgs boson produced in this experiment. So when you smash these protons against each other, a lot of things would come out. And because you can convert energy of the collision into creating the mass of the object you produce, then a lot of things that didn't exist before can come out. So it's sort of like you are smashing two light trucks against each other at incredible speed, and then comes a tank, which is much heavier, which doesn't exist before, but you can create new objects like that. So what you'd like to make sure then is that you can capture all of these objects that came out from this collision so that you wouldn't lose any information. And for that purpose, you again need to build a pretty humongous device called particle detectors. So what you see here is one of the 4 experiments that is being done at the Large Hadron Collider, or LHC. This is called ATLAS detector. And compare the size of this apparatus, you can see the size of people, for example, standing up here or standing down here. So you can appreciate the size of this device, which is like 20 meters high, 40 meters long. And because it's so big, this experiment has been aptly named as Atlas, because you might know Atlas is the Greek god that is big enough to actually carry the entire Earth. So it is meant to be that big. Well, not quite, but that's the idea. So Atlas Group has been very good in public outreach. This is the video clip they have produced before they actually started even building this experiment. And you see, this looks kind of similar to some of the movies you might have seen before. And this is the way they wanted to communicate this importance of international collaboration and how we actually managed to put together this amazing experiment. Now, this looks even more familiar to you, doesn't it? So this is the picture when this detector was being put together. 3,000 people involved in this from around the world, each of them building one part of the equipment, bring them together. We have to make sure they would fit with each other, so you have to actually do a lot of negotiations, discussion beforehand. And while in construction, you see this rather beautiful picture, a kind of symmetric shape, and it's sort of aesthetically appealing as well. Again, you see how big this is compared to a guy standing over here. And eventually this hall got completely filled up with high-tech equipment at the end of the day. And because this is kind of beautiful, if you look at it this way, this also affected the world of art and music in some way. And you might also see actually a picture of an opera being done in Spain, which is clearly inspired by this Atlas experiment. And I actually don't know what the theme of this opera is. It looks kind of very strange. But anyway, so even this kind of experiment has affected our culture and art in some way. So now comes the question to you. So when you build this big apparatus to detect all these particles coming out from the collision, why did we need to put together such a complicated object? So that's the question.